Good afternoon, everybody. Let's get started. This is the open house, open class for the USACO Gold class. Some of you I've seen in the silver class. That's great. So you want to take a look at this gold level, how different or how difficult the gold class can be. Don't worry about the difficulty level. I'll try to illustrate a few questions, hopefully without any other data structure or the algorithm, we should still be able to understand. The point is, you need to understand if you take a different approach, the questions may have very different complexity. Still solve the same question, try to get the same correct answer. If you do it in a different angle, different point, the complexity will be much different, maybe very different. So if you take one approach, especially we do it in the brute force way, you may take forever, running out of the time limit. But if you take a smart observation, you may be able to finish the calculation much faster. So we're not talking about the improvement, say 2 times faster, 3 times faster. So we want to write in USACO calculation, this magic number 10 to the power of 9, that's roughly the number of operations we can finish within the time limit. So for C++, we're allowed 2 seconds per each case. For Java and Python, we're allowed 4 seconds per test case. So this is the number of the operations we can finish. Normally, this would be a rough estimate because we just count the number of operations. The operations actually could be different. The integer addition would be cheaper than integer subtraction. Subtraction would be cheaper than multiplication. Multiplication would be cheaper than division or mod operation. And the integer operation could be, should be cheaper than the decimal operation. So we're going to add them together. The number of operations could be integer plus minus comparison, multiplication, division, mod, or even sometimes you need to do, say, square root calculation. So add them together. If the mixture is less than 1 billion, then very likely you should be able to finish the calculation within the time limit. You say, my number is bigger. Actually, I have, say, maybe 2 billion, 3 billion, but all the calculations, right, are just, say, integer addition. Then yes, you can have the number a little bit bigger. But if it's right, my number of operations, right, is 10 to the power of 12, then you know, right, this is way too big than this threshold, then probably does not help. If you reduce by half, or say my speed, right, has been improved by twice as faster. Why? If you divide this by 2, that is still 500 times 10 9. So if this takes 4 seconds here, right, this will take 2,000 seconds. So of course, right, USACO servers will not allow us to run 2,000 seconds till it finishes, right? It will just tell you, sorry, TLE. So whenever you see this TLE, that's time limit exceeded. So this will be treated as the same as wrong answer or failure. So even though, right, the answer is correct, but it takes longer time, still does not help. Okay, so this open class, I want to show a few examples, right? We're going to improve actually not from, say, this number that is too big than this one. We're going to improve by, say, improve twice as faster, or the improvement, right, can be 1.5, 2.3. These are important, can be useful when you have your number, right? 10 to the power of 9, that's the threshold, but mine has say 3.2 times 10 to the power of 9. Now, if I can improve, say 3 times as fast as before, then I can make it right roughly the same as this one here. Then yes, I can do it. But many times, right, you estimate, you know, right, this one is not 10 to the power of 9, rather this is 10 to the power of say 15. Oh, this one would be even bigger, right? So this one is say 100 factorial. Then you know, right, divided by 2, that's still way too big than this 10⁹. So we're talking about bring the complexity or the magnitude of the operations. Right. This may be say 10 to the power of say 20. I want to bring down to 10 to the power of 9. So this one is not divided by 2, 3, 4, right? You're going to say bring down the computation, the amount of calculation, right, by a factor of 10 to the power of 11th power. So normally you want to change, say from decimal operation to integer operation. That can improve somehow, but cannot make, you know, a factor of 10 to the power of 11. So these normally come from you work with different approaches. Change the viewpoint, then you're going to make it much simpler. And one thing that you have to keep in mind, right? If you have numbers like this one, 100 factorial or even bigger, that means most of the time you should tell yourself, I don't have to try all the possibilities. USACO, the contest is designed, you can find out the solution by checking each possibility, each permutation, each configuration, but you don't have to. There must be a different way. Either we don't want to find out which configuration, which permutation would satisfy the restriction. Rather, we're going to find out how many permutations would satisfy the restriction. So count the valid configurations versus enumerating all the valid configurations, that's different. That is actually many times the beauty of the USACO problems, or in general, the CP, competitive programming. You don't have to try each one. If the question does ask you to enumerate or print out all the valid configurations, then you know you cannot avoid. And you know, right, the number of the valid configurations must be a small number, cannot be big. But normally that's not the case. In USACO and also all the ICPC, the college level competitive contest, right? Or in general, any CP, the output normally would be a much simpler number, maybe just one number, maybe a few numbers. It will be very rare. You're going to read 100,000 integers. You can output 100,000 integers. It is there, but very rare, because this one is actually not for the, it does not encourage you to examine all the possibilities. So think about it. Calm down, you're going to find out a better observation, and that will lead you to a shortcut to the answer. All right, so I'm going to illustrate using this question. This one actually is well known. That is the max. Okay, I'm going to put it here. So that would be the max sum of any subarray. So what does this mean? Given an array A here of integers, you can say all of them are in the range, say from 1 to 1,000,000. And of n integers. N should be less than, or you could say 10⁵. Now find out find out the max sum of any subarray of A. Yeah, so it could be, so this is the array A here. You could try this part here, or maybe here, or maybe even on right, maybe like this one here. So try all the possibilities. It will go from position, say from position X to position Y. Right, X and Y would be in the range from 0 to, I'm going to start from 0. So this would be n minus 1. So one way to do this one is I'm going to run a loop. So the loop X will start from 0 all the way through n minus 1, and Y would be another layer going from X through n minus 1 here. When I say in this way, right, I'm going to make them inclusive. X starts from 0 less than or equal to n minus 1 here. Y starts from X here. Right, I want to make this one a subarray. When I say subarray, they must be continuous. You don't pick, certain numbers. If you do pick only numbers you want, right, you just pick the positive numbers. That's easy. That's very easy. So Y starts from X here, Y less than or equal to n minus 1. Now I want to find out the sum. This will be going from X all the way through Y. I'm going to write in this way here, X all the way through Y here. So if the sum is bigger than my record, so I'm going to have a record here, record initially, that's say 0. Why? If all the numbers are negative, I'll just take nothing, and then the sum would be 0. If the sum is bigger than R, I'm going to update R, right? So R should be max, this R here, and also this sum. So I could finish the question with 3 layers, the X layer, Y layer, and I'm going to find out the sum of A from X to Y. So that's a typical idea. But this one, I'm going to finish in 3 layers, X layer, Y layer, and then there's another layer Z, goes from X all the way to Y and add them together. But right, from the silver level, I don't have to do this one, another layer. If you do 3 layers, the number of operations would be roughly n cubed. Okay, we're going to have a detailed analysis why if you do 3 layers, in this case, the number of operations would be a constant C, which does not depend on n times n cubed. This n could be 1, can be 2, can be 1/2, can be 1/4, and so on. It's constant times n cubed. Okay, no matter what the n, right? If n is 10, if n is say 1/10, but this part is killing us. Why? If n goes to 10⁵, that's 100,000 here. N cubed could go to 10 to the power 15. This one is too big, right? To bring this down to 10⁹, the threshold, this one you have to divide by 10 to the power 6. But you don't have a constant C, right? That would be about 1 million. So now we don't want to do this 3 layers. As I said, right, we could reduce the number of layers from 3 to 2. Why? I can find out the sum of this array between position X to position Y inclusive. For this one, I can finish this one with just 1 operation using the prefix sum. Okay, suppose we can do that one. Then how many operations I need to run for the 2-layered version? right? I still have X layer and I have the Y layer. When X is 0, Y goes from 0 to n minus 1. So Y has n iterations. When X is 1, here, Y goes from 1 through n minus 1. Y still has n minus 1 iterations. And all the way to n minus 1 here, this one has just 1. When X is n minus 1, Y goes from n minus 1 to n minus 1. So that's 1 operations. If you add them together, so this one, if you add 1, 2, all the way through n, that's still n squared plus n over 2. So this one is, again, a constant times n squared. In this case, the constant is actually 1/2. I'm going to drop the other part here, the n over 2y. This part is much smaller than this n squared. So normally when you try to estimate the number of operations, we're going to take the leading term, or the part that is the majority. So this one, you can see when n is 10/5, this one is in the order of 10/10. This one is in the order 10/5. So 10/10 versus 10/5, this one is much, much smaller than this one. So we're going to just estimate this one here. So this C is 1/2. N squared can go to 10/10. So divided by 2, that's still 5 billion. That's still much bigger, right? Actually, rather than just have the iterations, right? Each time I have to do the find out the sum of the array A between position X and position Y and check the record. So you still have to do maybe 2, 3 operations here, 1 more operation here. So that's 4. 4 times the 5 billion, that's 20 billion operations. That is too much. So this is the number of operations we have after we have taken the prefix sum. The prefix sum, or sometimes you can use the partial sum. Either way, it's fine. And I'm pretty sure, right, many of you have been exposed and have practiced the skill, the prefix sum, so that I can get the sum of the array A between position X all the way through Y in just 1 operation. Okay, we made progress, but still not enough. I still want to find out the max sum of any subarray of A. That means you still have the X and Y arbitrary, as long as X is less than or equal to Y. Any such interval, if the sum is the maximum, I want to report that one. So maybe the sum is not, the subarray may not be unique, but the maximum sum should be unique. So let's take one example here. Suppose I have 1 and 2 here. This one is -10, and I have a 3, and then I have a, say, -4. So here, right, if you take this subarray, the sum is 3. If you take this sum, it is 3 here. And actually, that would be the maximum. Why? Because no one would love to include -10. This one is a hole, right? Too deep. If you want to include it, right, you have to use a lot of the positive numbers to make up the hole here. So far, unfortunately, no other integers, right, would be big enough to make up the hole. So here, the max sum should be 3 here. So one interval, one subarray right here will contribute to the max sum here. Another subarray here consisting of just one integer, right, also has the maximum sum 3. Okay, so for a long time, this question, find the max sum of any subarray of an integer right here, people thought the best algorithm, we're going to do this one n squared. You could improve the C, make it, say, divided by 2, divided by 3, divided by 4, but still, that's not enough to finish the calculation in the time limit. And then one day, this question, actually, there are many versions of this story. One version goes like this. In a party, People are talking about this one and then bragging, okay, I can make this C smaller, right? Still it is C times n squared for the number of operations we have to take to perform to find the max sum. So some are bragging, right? I could make this C smaller than yours. The other one said, right, I can make even smaller than yours under certain case situations. And then a person heard about the story and then was in a party and then took the beer. And before he finished the beer, he told the people around, I think I can do better. He said, I'm not trying to make this C smaller, but I can bring this exponent 2 down to 1. So the idea, right, is I'm going to bring down from the C times n squared to another constant, you say C prime times n. Now, people are really surprised and also very interested, saying, how come? We thought this one, you do have to check all the subarrays. That means, right, all the intervals from x to y for the indices. How can you just do n here to the power of 1? That means you're not going to check the pairs x and y. If you do check the pairs x and y, then you have to make it n squared, right? That's easy. If you pick two integers, right, from 0 to n minus 1 here, so you have n, actually n plus 1 choices, picking 2, that's always n squared. How come you make this one just n, not the pairs? Actually, the person, right, still holding the beer said, okay, let's do this one here. The idea, I can write it down here, it's not too complicated, but it actually works. So I'm going to just use the corner here and it works. So here I still say R is 0, the record, right? The maximum sum of any subarray, the record is here to be 0. Again, we're going to assume, right, if all the numbers are negative, we're going to take 0. That means you don't take any subarray and then the max sum would be 0. Otherwise, if you don't like this definition, right, you just say, okay, if all the numbers are negative, just take the largest number in the array. That's also, just go through each element just once. That's fine. So I'm going to take this one here. And here we'll still just say try x goes from 0, x less than n here, x plus plus. So if I set up the loop like this way here, right, you know, this will be just one layer, and then the number of operations should be some constant times n. How big is constant? This would be depending, right, in the body of the loop, how many operations I want to perform for each iteration of this x loop. Okay, so here I'm going to do, say, you can do int or you can say long. So sum is 0, and also this one also try to make it long here. So this one, it says, right, sum plus equals a x here. And of course, right, we're going to do the update, right? So R should be math.max. By the way, I'm going to use either way here. So just any position max, this R would end sum here. Okay. And if sum is negative, I'm going to set sum to be 0. And if you do C++, you're going to change this one to long. Okay, that's all. The code is short, but I claim it's working. So suppose, right, you're in the party, the person who told the others, right, okay, try this one here. Do you think this will work? Well, the beer is still in his hand. Okay, let's try this example here, right? Can I find out? I'm going to change the color here. So I'm going to find out the 3, right? The maximum sum of this array. And I'm going to go through this one just once. Let's try whether it's right. Initially, R is 0, sum is 0. So when I try x being 1, right, sum is 1 here. So I'm going to just use s. So s in this case, that's 1 here. S is bigger than R, so R is 1. Now, when I'm at this point right here, x is 1 here, sum plus ax, right? So sum should be 3. 3 is bigger than the record r, so r is 3. Now x is here, so ax is this -1, -10 here, right? So sum becomes -7. -7 is it bigger than r? No, I'm going to still keep it. So r is still 3. Can I move this one? Okay. But here, right, if sum is negative, I'm going to make this one to be 0. Okay, a little bit weird, right? Why, if it's negative, I'm going to make it 0. Okay, let's keep going here. So this time, right, x points to this one here, ax3. So sum, I'm going to say increased by x. So now sum is 3. 3 is bigger than r. The record, right, still here. That's fine. And the next round, right, x is here. 3 plus -4 here, right? S is -1. Is it bigger? No, I'm going to still keep r here. And actually, s is negative. I'm going to make this one again 0. So here at the end, right, I do have this r to be the maximum sum. You can change the numbers a little, right? For example, I'm going to change this one, say, to be 4. And it's guaranteed you're going to find out 4 here. Okay, so clear, right? So this new method, try to solve in the maximum sum of any subarray. Clearly, it is this time some constant times n. How many operations here for each iteration of the X loop? 1 operation plus 1 comparison assignment 2, comparison assignment 5. So 5 operations. So this C prime actually we can say, right, is 5. Actually, it's not complicated, right? Just do the integer addition and also the comparison. So all the simplest operations, 5n. So 5n versus this one, right, is a half n squared. So when n is 10, 5, this one is half n squared. That's 5 times 10, 10. 5n, this would be 5 times 10, 5. Of course, right, this one is much less than this one here. That's what we want to do. Bring down the complexity or the number of operations, not divided by 2, divided by 3. Rather, we're going to bring down, right, from the magnitude here, 10, 10, bring down the exponent 10 down to 5. So, right, if for the purpose of USACO, right, if you can bring down the exponent lower than 9, then we're good. We'll be happy because we can finish the calculations within the time limit. All right, so this is just one example, and this algorithm is called the cadence algorithm. So it is a smart idea. Going from, right, we see have improved from 3 layers to 2 layers. Now just go to 1 layer. Okay. We're going to come back to this question maybe later, but I want to leave you this one up to you to think, right, why this statement here, this statement actually is amazing, right? If sum is negative, we're going to set sum to be 0. This part, right, you understand, it's still the prefix sum, right? Initially, sum is so far the prefix. You're going to increase by AX, right? So we're going to say update the prefix sum and update the record R. That's also natural. Sounds reasonable, right? Only this last line here in the body, like a miracle, it solves the question for the max sum of any subarray. So I'm going to leave this one to you to think about it. Why this makes sense? And from here, what can we learn? Right? Maybe later, you're going to learn something from here and propose or design an algorithm that will help your question or help a project you're working with. All right, okay. Also, this is the format for the USACO Gold class that we're going to take. Most of you would come from outside of Texas. We're from Houston, Texas. Many of you would be from the East Coast, West Coast, North. So we're going to connect through the Zoom, and even some students may sit in the physical class. Actually, no, for Gold, we don't have anyone. We're going to use to connect all the students. You should be able to take notes fast, right? So there is a save button on the annotated bar. So saving the notes would be very convenient, and you can have a lot of thinking after class. So take notes, organize the notes, and organize your code after class. That would be very important. I did not mention, right, in the current setup, the promotion from silver to gold, from gold to platinum. Now it's getting harder than before, especially when a lot of students with strong math background are joining this contest. So it is getting harder. So competition gets even more fierce, more competitive. So be prepared. All right, so save this one here, and I'm going to clear. Now we do have another question. This is also what I would encourage you guys to do. So this one is a little bit different. Still is a max sum array question, but this time we're going to do the circular array. This time array A still has n integers. Find max sum of any non-empty circular subarray. Okay, this time empty array, empty subarray is not allowed. If all the numbers are negative, find out the smallest, find the biggest negative number. Okay, again, array A has n integers, n still is restricted to 10, 5, 100,000. All the numbers this time. Oh, last time did I say the, no, that's wrong here. So this one actually should be, take it back. This one should be negative 1E6. If you don't have negative numbers, that would be trivial, right? So negative 1 million to positive 1 million. Okay, excuse me for that mistake. Take back. So here, all the numbers are again in the range from negative 1 million to positive 1 million. Now report the max sum of any non-empty circular subarray. So why this one is a little bit different, your array can go around. So here, let's try this one. We're going to have a circular array. So we're going to have, say, negative 2 here, and 10, 11 here, 10 here, negative 20 here, 5 here, and negative 3. I can make this one small. Okay, I can spread them further. So 11 here, 10 here, negative 20 here, and 5 here, negative 3, negative 5, 8, negative 13, and there is a 10. So that means, right, our array could go like this one here. Right, if we start from here, going this one, actually, this is an array that will give us the maximum sum. So if you add them together, right, that's 31 minus 2, 29 actually is the biggest. But if you start from here, right, in the previous setup, we cannot. We can only go here. And then this negative 20, right, we're not going to do it. This hole that is too big, we're not going to do this one. So I'm going to do 21 minus 9 minus 2. That's 19, the biggest. And then we might have 8 here. We don't. So 19 would be the biggest. This 10 would not be able to connect to this -2 and 11, 10 if this array A is not circular. Now we're going to allow this to happen, right? This -2, 11, 10 is allowed to extend this way here to the end of the array 10. So now this can be bigger than the previous one. That previous one, the version should be 19. Now we're going to make it 29. So with such a modification, how would you do it? Good. See here. That's a very good idea. Okay. Yuyan has a suggestion. So, okay. So let's try this idea. Yuyan says we're going to do this one. Suppose this is the array A here. Goes from 0 to n minus 1. And we're going to double. So make another copy here. So this is the copy, still goes from 0 to n minus 1 here. Now we're going to find out the max subarray no more than size n. So we're going to find out, let me change the colors. So should be, okay, let's do the red. So find out any subarray from x to y, as long as y minus x is less than or equal to n minus 1. This time you can say, right, this one is actually n. This one is 2n minus 1. So we have an array of size 2n minus 1. Find out the max sum of any subarray where the length is no more than the difference of the two indices, right? No more than n minus 1, or the length of the subarray should not be bigger than n. So how do we estimate the number of operations here? Right. Suppose giving you one subarray of length n, so going from 0 to n minus 1. So what we try to do here would be, let me erase this part here and change the color. So we're going to fix, right, from 0 to n minus 1, you're going to find out any the maximum subarray here. From 1 to n, find out the maximum. From 2 to n plus 1, you're going to find out the max, right? From 3 to n minus 2. From the last one, you don't have to go from n to 2n minus 1, but you might try n minus 1 to 2n minus 2. Okay, remember, right? The best we can do here, this one takes n, right? A constant times n. So here is c times n here. This one, you also have to do c times n here, c times n here, c times n here. This one also c times n, right? How many such intervals do we have? We have n of them. So this one is c times n times n. That is still c n squared. N can go to 10.5. So this one actually does not work very well. So still it will go out of time. Okay, the idea is correct, but this one still is not fast enough. Okay, let's try. Okay, X has a, well, in the real class, right, you're not going to have just X here. You have to use your real name. Anyway, so the suggestion says we're going to go clockwise and counterclockwise. Double the time. Double the time. Still not clear. I think I could interpret your suggestion right, and also interpret not right yet. But I think this could go on the right direction. So go clockwise and count clockwise, CW and CCW. All right, in the gold class, for such times, I would break the class into smaller groups. And there is a very convenient feature, the breakout rooms. So I can put you guys already into groups of 2, 3, and each group will have a separate room. So I would visit every room and try to join the discussion. So if you have an idea, right, how would you implement this idea? Or if you have trouble, say got stuck in the coding, try to find out what went wrong and how to fix it. So that would be good. But for the coding part, normally that will occur at the beginning of the class. Normally we're going to spend about, say, 15 minutes, 20 minutes trying to figure it out. Okay, Jack, any question there, right? Jack says, okay, I do have a debugging problem. Anyone can help me, right? Or John says, okay, I have an idea, right? This one, I think it'll work, but turned out it does not run smooth. Anyone can see my problem? So that is the place. We're going to exchange the ideas. We're going to also see how others are solving the questions. It's guaranteed, right? Different people will have different viewpoints. That's actually, I would really, really want to advocate. Always think from different viewpoints. Other people's ideas, many times, maybe they did not realize, but for you, will give you the insight. You say, wow, I've never thought about that way. And hopefully, right, once you get that idea, the hint, right, that opens a brand new door or opens door to a brand new world. So many times I found that's exciting. Okay, Ali has an idea here. Normal way with doubled, but chop off whatever goes over. Afterwards, do the operation again to get rid of the training negative on each end. Okay, I think this one also is in the right direction. So let me show, right? This is actually, we would think hard during a contest. Oops, you guys are typing a lot. Okay, okay, let me see here, X. Okay, I think X, you're in the right direction to go ahead. You're getting closer. So here is one observation, X is right. So you have this array A here. To get this max sum, right? From any array here, right? Any subarray, either the subarray will turn around or it does not, right? You might have some, right, going from position X to Y here, where Y is bigger than X. You might have something that is opposite, right? You're gonna go from Y to X. What does it mean? Right, Y is bigger than X. But you say, what does that mean by going from Y to X? Because you're gonna go from Y to the end here, right? And then come back to 0 and then going to X. Okay, 2 more messages. Okay. Do it without circular sum. We're going to do just as we did for the cadence algorithm as before. Okay, Alice's idea also very good, getting closer. Brandon. Okay, Brandon's idea and Alice's idea are actually very close, very good. I like it. So have you thought about, right, the idea? We say, suppose we try to do the subarray not wrapping up, actually X idea, right? No wrapping. So just go from X to Y. That's easy. We can do it in just one round, Cn, that will finish finding out the max sum of any array that is not wrapping around. Now, can we do this one, right? So if you want to get from, say, Y to N minus 1 and back to 0 and X here, right? That means you're going to consider all the subarrays that will wrap around at N minus 1 here. I don't want to do the two intervals, right? For every X and then for every Y and do every X, that will still make it N squared. I don't want to try that one. Rather, try this idea. Any subarray that wraps around N minus 1, you're going to have part of it, right, going here. I'm going to use a different notation here. So part of it, right, will go here and it will continue back here. Okay, let me use this diagram here. So a subarray that will wrap around, you're going to go from 0 to somewhere here, right? And then somewhere here going to N minus 1 back here. But I don't want to try all the X and Y here. So what I did, this part is, this is actually the prefix sum. This part is the suffix sum. At any point, say position J here, I'm going to go still 0 to N minus 1. At any position J here, find out the max prefix sum. You can say including J. Including J, what is the max prefix sum? Now from position J plus 1 to the end, what is the maximum suffix sum? Right, so many of you have been exposed to the prefix sum, suffix sum, and also the maximum. If you want to find out the max value of an array, say B, going from 0 all the way to any index position X, this one can be found in O1 time, in a constant time. You don't have to check one by one. Once you fix this left end, this can be done. You can save the value so you can retrieve it in just one operation. The same, if you want to find out going from Y all the way to N minus 1 here, this one can also be retrieved in just one operation. So now for each J here, we're considering the subarrays that will wrap around at N minus 1 coming back here, right? So must have one part that is the max prefix sum. that is also the max suffix sum. Because we guarantee, right, the prefix will start from position 0. The suffix will end at n-1. So these two, they're going to glue together if you allow the circular array. So for each part, right, PS here, right, the max, I'm going to take O1 time. The suffix SS will take O1 time. So we're going to run a loop J, n iterations, each one take a constant number of operations here. So this part, considering the wrapping around subarrays, also will be a constant. Let's say C2 here times n, plus the part, we're going to consider the subarrays that do not wrap around, that takes also C1 times n here. So together, this would be a C1 plus C2 times n. C1 maybe 5, maybe 10, C2 also maybe 5, maybe 10. So still together, right? Maybe 10, maybe 20. So another constant C3 times n is 10.5. So this one still we can finish within the time limit. Okay, maybe a little bit fast, right? But I want to, okay, Alice's question, right? We're going to do the subarray, two cases, right? Either the subarray does not wrap around, that means x is less than y. X is bigger than or equal to 0, x is less than or equal to y less than or equal to n-1. So here, that's the typical, the max subarray with the max sum as what we did in the previous version. So the array does not allow wrapping around. Now we're going to do another case. The subarray does wrap around going from n-1 back to 0 here. So let me erase this n and the 2. Actually, I try to remove the 2. So here, this would be 0 here. That would be n-1. So this subarray, it will go somewhere here, reach n-1 and back to 0 and then going to somewhere here. So this is a subarray that will wrap around. So to find out this one here, right, I want to find out at any position j here, what is the maximum PS? So you're going to build an array PS, the prefix sum, and you do another one, the max PS, the maximum prefix sum. Okay, the construction of the partial prefix sum, that's on time. Find construction of the maximum prefix sum also takes on time. The same thing, the suffix sum takes on time to build, and then the max suffix sum also takes on time to build. So you can retrieve, right, at any position j, what is the maximum prefix going from 0 to j, right? And maybe here, maybe here, maybe here. Okay, find out the maximum prefix sum. Also find out the maximum suffix sum from j plus 1 to the end. Right, this one may be from here or maybe from here, but anyway, so this will include this one and the index n-1, so it will just go around and meet 0 and go forward. So this will include all the subarrays that will wrap around. The red subarrays, right, they do not wrap around. So only 2 such cases of the subarrays. Each type, right, the red ones will take constant times n time. The subarrays that do wrap around also will take constant times n time. So together that would be constant times n, which would be very much smaller than 10.9, the threshold. So we can finish this calculation within the time limit. Okay, anyway, so maybe this one running a little bit fast, right? Anyway, I'm going to show you, walk you through one way to implement the idea. So I'm going to save. Oh, it's 58, time flies. You know what? I'll just send you the code. So here, this part is the non-wrapping, the cadence algorithm. This part is the prefix sum, and you get the max prefix sum. the suffix sum and get the maximum suffix sum. So here, right, construction is just each one takes one operation. This one, each entry takes one operation. So all of them would be big O(n). This one, the same thing. And then you're going to say the minimum, the maximum prefix sum here, and also the maximum prefix sum. The maximum suffix sum, the maximum prefix sum, add together and update the answer. So that would be the what we're going to do. So here, this part, we say big O(n). We're going to talk about the big O notation when we start the gold class. This part also big O(n), this part big O(n), this part big O(n). So all together, overall, that's still big O(n). That means a constant times n operation. So we can finish this one happily. Okay, so let me send you the code. This is the max. The maximum sum of any circular array, and it's done here. All right, so we run a little bit fast. Time does fly. That's why in the USACO class, we can make it very interactive, and without noticing it, right? Time is up for 2 hours. So hopefully we're going to have a happy and very productive year. And then even though the contest is getting hard, I hope many of you would take the opportunity and then get promoted to the platinum level. I want to mention, right, from the statistics, so far in the past 6 years, 6 seasons, for all the female students, all the girls in platinum, nobody missed the ideal university college. For boys, I cannot have that confidence. Boys, well, if you can get very top in the platinum ranking, you still have very, very good chance. And of course, right, if you are invited to the summer training camp, of course, no exception also. So try your best to get promoted and also try to improve your standing in the ranking nationwide. If you can get the nationwide top 100 platinum, then your chance would be very big. Of course, right, if you choose your major in STEM when you apply for colleges, this is always the case, right? You did so well in math Olympiad, physics Olympiad, computing Olympiad, but you choose to do history in college, probably that does not help you much, right? But if you do choose STEM, USACO actually carries more weight than USMO. That's the feedback I have from a lot of the admission officers. I have direct and indirect contact. Actually, for this one, we don't mind you do in Java or C++, but both languages are supported. You can do either way. And actually, I would encourage you to do both languages. So sometimes you would start from C++, sometimes you would start from Java. Try to, write in both languages, because doing well in both does not hurt you. It will only help you. Yes, actually, not just gold, every level from introduction to bronze, silver, gold, all would take 1 year, and platinum actually now would take even longer. As long as you stay in platinum, you're going to stay there, because there is no other way to for another promotion. And actually, we try to recommend to add more levels, right? Platinum was added in season 2016. Before that one, only gold, silver, and bronze. And we think it will help students and also parents if we have more levels. Like when you play Go, even for professional Go players, right? There are 9 levels. If you play chess, there are more levels, right? You start from say everybody, right? If you start from say 500 and then 1,000, 1,100, 1,200, all the way say 2,000, then you're very good, right? When you achieve 2,500, wow, that's amazing. And if you can go over 3,000, you are world famous. So no, there is no penalty. Once everybody starts from a bronze, right? Once a silver, always silver. Once gold, always gold. Next time you start the join the contest, right? You're gonna start from gold. Once a platinum, always a platinum. So you never go lower. You can only go higher or stay. Yeah, that's actually, I think it's feels better rather than in math, right? Last year you qualified for AMY. This year you still have to run AMC 10, AMC 12, and try to qualify for AMY. Even last year, right, you qualified for AMO. This year you still have to work from the beginning. So I think in terms of the college application, this one actually, I think it's better in terms of the the amount of the effort you spend and also the help you can get. Yeah, you're right. Actually, USACO now gets more attention from college students because when you try to do job interview, especially for the big high-tech companies, Amazon, Google, Microsoft, Facebook, right? You have to go through the step, especially right if you want to do the high-tech, the big data, you need to work on the questions corresponding to the gold level. Many of them would be in the silver level, and some of them could be at the gold level. So a lot of the places, right, website like LeetCode, I would also recommend you guys to try. The problems would be the must-go website for the people try to get a successful interview at the big FANG companies. So if you have the training before college, you have the advantage, right, for your college application. You also have the advantage for your job interview after college. So that's one stone, two birds. And actually, right, if you later your career, your life, right, is in the big data job, big data, artificial intelligence, that also be very, very helpful. So I say one stone, right, three birds. So just take advantage of this one here, and hopefully this will be very useful, helpful for your lifetime. All right, okay, I'll stop here and hope to see you guys in the near future. Bye. Sure, you're welcome.